Good day. So in this session, we will be talking about work and kinetic energy. Okay. So uh, in the last presentations that I have, as I recall, you learned about the concepts of Newton's laws of motion. Of course, its applications on statics and dynamics. So today we are going to have a work in kinetic energy. So we are going to utilize this PowerPoint presentation made pre-made. Okay, so the author of this book actually is James Walker. Okay, so the this chapter consists of work done by constant force. Then so we have here the topic outline, then kinetic energy and work energy theorem, then work done by a variable force, and of course power. They're actually related. Okay, so work, energy, and power, okay, so they are related. Okay, so first we have to define what is work. Okay, so you might think that in our day-to-day living, it has the same meaning with work in the concept of physics. Okay, so work basically is the product between the force and the displacement. Okay, so there is work done on the system whenever the force. Okay, so whenever the, how do you call this one, I have, where's my ball pen? I'm going. So so there is work done on the system if the force and of course the displacement are parallel. So they must be parallel with each other. If they're not parallel with each other, then we cannot define work. Okay, because later on you will see that aside from having this F times D, later you will find this cosine identity. I mean, this identity, this trigonometric identity, which is cosine. So cosine, okay, so whenever cosine is 90, that is equivalent to 0. Cosine 0, cosine 180 is equivalent to 1, and negative 1 respectively. Okay, so that's it. And by the way, the unit of work is joule. You have a Newton meter. So you might think that um, work and torque are just the same, but no, they are not, because torque basically is a vector quantity. That is why you have their meter times dotted to Newton. Okay, to separate it from the unit of work, which is Newton meter, which is equivalent to joule. Okay, so you have there, and then you have here basically the equivalent work by the different sources. Okay, so you have here the energy use, the eruption of Mount St. Helens, then even in melting ice cube, so you have here the amount of work, then and so on. You can apply work in different systems, which involve, of course, energy absorption or dissipation. So later on, you will know how energy and work are related with each other. Okay, so if the force is at an angle, the figure earlier shown, the man is pushing an object, and the force and then the displacement are parallel. However, in this example, the force applied is basically at certain angle. So you have here. So all you've got to do is just to take the component of the force. So you have here the force going to this direction. You have that force there. So you're going to take the component of that force, which is basically parallel to the displacement. So now you have here the component of the force, and this component of the force is basically what we call as the F cosine, of course, the angle. It's a theta basically. So how about the component along Y? You might be asking, what is the purpose? Is there work vertically? Well, no. Why? Because this component of the force is uh, doesn't doesn't make the object move in parallel direction. They're actually perpendicular. So remember, cosine of 90 is 0, so there is no work done on it, on the object. So the force, the component force that gives work on the bag, or that how do you call that one, on that object generally, is the component of force along x. So they should be parallel. Okay? Again, work and displacement should be parallel so that we can define work. Okay? So in this case, we should bear in mind that the product of, if you're going to recall, the dot product between two vector quantity is basically a scalar quantity. So meaning to say that this work here is a scalar quantity. So it is a scalar quantity. Wait, I just wanted to have my eraser. There's no eraser. Anyways. Okay. So you have there. Then, so this is what I'm telling you a while ago, that the the dot product of force, I mean two vector quantities, the resulting quantity is a scalar quantity. Okay, so in this figure, you might be thinking, you might be asking, who does the work? Because later on, you will be asked, who does the work? We to where the work is done. The work done by and the work done on. There is a big difference between these two terms, work done by and work done on. In this figure, as this guy here slid down from the ramp, this case, it is actually the gravity who does the work. So the gravity does a positive work on this person. Okay, so the work done may be positive or negative, or it can be zero. That's what I'm telling you a while ago. Whenever the force and the displacement are parallel with each other, then the work must be, I mean, perpendicular with each other, the work must be zero. Okay, so whenever the force and displacement are parallel, okay, but the angle is less than 90, okay, that will gives you a work which is greater than zero. But whenever the work is, I mean, the angle between displacement and the force, I mean displacement, yes, displacement and the force is greater than 90, it will give you a negative value of work. When can we say that the work is negative? Okay, and in what scenario wherein we can visualize that the work is negative? Okay, so just try to imagine if you're going to push a box. Okay, say you have here this how do you call this one? Okay, you have here this surface, then you have here this box, and if you're going to pull this one, you're going to apply force, okay, on this box. Of course, it will move in this direction. It will move in this direction, follows the direction of the force. However, we cannot just eliminate the friction element. Okay, so meaning to say that in the floor, since there is surface contact, then we may define what we call as frictional force. Friction. So there should be friction. And where is the friction directed? Well, the friction directed to the left. Okay, so you have here the frictional force. Okay, so in this case, if you have here the frictional direction, and then you have there the displacement. So you have here the displacement. Let us note that one as D. Then the friction and the displacement should be in opposite direction, and the angle that exists between the frictional force and the displacement is basically greater than 90, or should I say 180. If you're going to take the cosine of 180, this case, you will come up with negative 1. And that's the time that we can say that there is negative work. Okay? So you have there. Okay, so so if there is more than one force acting on the system, on the object, then you've got to take the total force acting on the system. Okay, so in this case, if there are if there are multiple forces acting in the system, you have to take the total force, or in second law of Newton, that is the net force, because the net force will tell you the direction of the displacement if there is displacement. Okay, so you have there. So there's a lot of forces acting on this car. So you have here the drag, basically the resistance due to air. Then you have the frictional force. Then you have here the normal force. Then you have a component of the weight, or the weight, should I say. Okay? So what is the net force that causes the object to move, or to gain displacement? Force, that is this force here, the net force in this direction. How about vertically? Okay? Well, perhaps you can never see a car which flying or moving vertically. Okay? If we're going to superimpose this one in x and y plane, or the coordinate system, then the force should be the car should be moving how do you call this one, horizontally. Okay, unless if you have a car which is designed just like what Bulma did in Dragon Ball Z. Wow, oh my god. Anyways, so you're just going to take the total force acting on the system, then you have there the displacement multiplied to that particular force, or if the force is needed to be decomposed into its components for us to get the parallel parallel force to the displacement, then you apply this identity. Okay, so the work and energy theorem. Work and energy are actually related with each other. Take note that if you're going to push an object, it will move. By the time that you are going to push an object, the object gains a velocity. Okay, so velocity can be correlated, or can be associated to what we call as kinetic energy. Okay, that is basically defined to be the energy in motion. So you have there. Okay, so you have here the work kinetic energy theorem. So this one. Then doing some algebraic manipulation. Okay, whenever you're going to apply work on the system, then that is equivalent to the, how do you call this one, the change in the kinetic energy, or the kinetic energy state of the system. So we have here the definition of the work energy theorem. So therefore we can say that work and kinetic energy, or work and energy, are associated with each other. Okay, so you have here. So let me find if I have, how do you call this one, highlighter pen. There's no whiteboard in here. Let me see if I can move this one. Then okay, so again, I think there's no whiteboard in here. Okay, anyways, now if you're going to look at the work, just work is equal to force times displacement, or delta x. Force, we can have this one as m a times d. Okay, so you have there. Then if you're going to look at if you're going to decompose If we're going to decompose acceleration, then we will have mv over t over t, or we can even have this one as dt, dv dt, and then times d. We have here this one as delta x, something like that. So just don't mind about the notation. Well, it's supposed to be this one. This should be delta x displacement. So we have v over delta t, change in time, times you have here dx. Okay, so dx and dt, this one here, we can define that one as mv, then another v here, dx over delta x over delta t is v, so that is why you have mv squared. So this is basically the derivation using algebra. Okay, so you have there. Then you have there the work energy theorem. Like, if work energy theorem states that the total work done on the object is equal to the change in kinetic energy. So let's say this is the work energy theorem. So you shouldn't bother yourself about, okay, this equation is quite complicated. Well, no, this is not actually complicated. It looks complicated, however, if you appreciate its beauty, if you're going to look into the beauty of this work energy theorem, well, you will be able to appreciate this. Okay, how are you going to look the beauty to look into the beauty of this equation? Of course, by applying this in problem solving. Okay, so so the work can be quantified using, or can be interpreted using a graph. Okay, so where in the work basically is the area under a curve, or under a, yes, a curve, because this one we can generally term this one as a curve, straight curve, something like that. Anyways, so this area here refers to the work done on the system. So notice that this is a square basically, or this is a regular polygon. If you're going to take the, how do they call this one, the area of this, so you're just going to have the, say, the height and the width, which is basically your d. So multiplying this one, so you have a is equal to f times d, which is basically equal to the formula of force. Okay, so therefore the area in the curve, under the curve, bounded by these points, of course, is your how do they call this one, work. Okay. So if there are several forces acting on the system, then all you have to do is to take into account the areas if you're going to use a graph. Okay, so the area of this force plus the area of this curve plus the area of this curve, and that one will be equal to the total force acting on, total work acting on or done on the system. Work done on the system. So you have here. So if the work applied is somewhat looks like this, then you're not going to use algebra anymore. Rather, you are going to use calculus. Okay, so that's it. So say this is the work 1. This is work 1, this is work 2, this is work 3, this is work 4. Then with that, all you have to do is just to take the work total to be work 1 plus work 2 plus work 3 plus work 4. Okay, so you have there work 4. Okay, so if the work done on the system is negative, of course it becomes negative. Okay, so in this case, this is greater than 0, therefore the work is greater than 0. Okay, if the work is under 0 or below 0, should I say, of course you have to take a negative. Okay, so that must be the work, the force, the work done by a force which is opposite to the displacement. And one of the best example of that is frictional forces. Okay, so you have here the variable forces. In this case, in calculus, there is a theorem that you're going to use, such that you're going to take to treat these variable forces or these areas into infinitesimally small rectangles, then add them up. So that's it. Then this is the work. Okay, this is the work on the stretching spring or rubber band or whatever. So you have here, so the work done in stretching the spring can be expressed in this equation. Work is equal to 1/2 kx squared. There is actually how do you call this one, a derivation of this, but I have a hard time in writing this one in this small how do you call this one, screen. Anyways, so this is the work done by the the work done in stretching a spring or a rubber band. Okay, if you can still remember the concept of Hooke's law, you have Hooke's law that is equal to kx. If you're going to multiply this one with the displacement and integrate that one, then you will be able to get this expression. Okay, there is actually derivation to this. Okay, so anyways, so notice that the force as you apply greater force, then the x here also increases. So with that, the work is then associated with the displacement. Okay, that displacement refer to how stretched the spring or the rubber band is. Okay, so in terms of power, so when we talk about power, basically this is just but the ratio between the work or energy or the work done per unit period of time. So how much work is done per unit period of time? The greater work that you're going to do in smaller amount of time, or yes, mean to say that you have high power. Okay, it is your ability. Yes, you can do work, but how long are you going to do the work? If you're going to do a particular work in shorter period of time, then we can say that you are more powerful compared to those who do the same work in longer period of time. Okay, so in this example and in this equation, we may add actually E over T. Okay, so power actually is not limited to electricity, but whenever you're going to transfer, say, an object from one place into another, you can also compute for your power. Okay, by the way, I forgot something. Let me go back to this presentation I have in here. So their work, there's displacement, but you are not doing work. For example, if you're going to lift a bag from the floor, then you're going to walk lifting the bag. Actually, you are not doing work on the bag, vertically or horizontally. If you're going to lift the bag, say you have here a bag, then you're going to lift that one, then bring that bag somewhere, So you are now covering certain displacement. Okay. So in the duration of the transfer, in the travel, along the travel, you are not doing work on the bag because the force that is used to support the bag is going upward while your displacement is going uh, horizontally. So they are perpendicular with each other. Okay, so that's it. I forgot to cite that point there. A concrete example. Okay, so going back here. So you have here the unit of power. You can have here joules per second, or that is equivalent to 1 watt, or 1 horsepower. In our vernacular term, this one is what we call as caballos. Caballos. Okay? So there is actually a way made in order for the relationship between watt and horsepower. Okay? So there's a method used. Okay? They're actually using a horse. Okay, so you have your power. Then you have here the sources, typical values of power. Okay, so you have here human brain. So you have 20 watts. Okay, so human brain have basically lower power values. Okay, so the power on an object moving at constant velocity, so you have there. So the power then is equivalent to F times velocity, the force. If we're going to imagine an engine or say a car, so the force actually comes from the engine, then its velocity. Okay, so meaning to say that the faster you move, the more powerful you would be. So if a car moves very, very fast, then you have very, very high power also. If you're going to move at infinite velocity, then you also have infinite power. But again, we cannot attain this certain value. There is a critical value wherein the classical mechanics is limited only to. Okay, so this is basically the classical mechanics concept dealing with power and of course moving object with constant velocity. Okay, so for this summary, so you have here the equation for the work. Okay, and work is a, how do they call this one? Work is a scalar quantity. If there is a multiple work present in the system or multiple force acting on the system, just take the total force. Okay, so you have there, and then also the unit of work, you have joule. So if the unit of work is joule and work is related to energy, then the unit of energy must also be in terms of joule. Okay, so you have there. This is the equation for spring forces. Work done on spring, work done by spring. Okay, so work done on spring, work done by spring. So you are just going to take to be careful with these terms. Okay, so in the next presentations that I will be having, we'll be dealing with the application of work, okay, into certain problems. So with this presentation, I'm going to I'm hoping that you learn something out from this. So for uh, that's all for this session. So